Okay, uh, now we start chapter 1, which is Introduction to Quantum Mechanics. And this is a very important subject. Quantum mechanics is a very important subject, and it's a subject that is covered in uh, maybe at least one or two courses in physics. Uh, and it's a very involved subject. However, it's a very basic subject for studying phenomena at a very, very small scale. Phenomena at the scale of atoms and even smaller. So it's a very important type of mechanics. This is the classical mechanics. Why do we teach quantum mechanics in a course like this one, in a course that deals with, say, nanoelectronics, nanotechnology, or solid-state electronics? Because we will be dealing with very small particles, very small objects at a very small scale. And we'll be dealing with motion, again, at a very small scale. And that requires this type of mechanics, which is quantum mechanics, as opposed to classical mechanics. So we will try to overview and give the student here a flavor of what quantum mechanics is all about. I'm going to do quantum mechanics at this service here by teaching it in maybe a few weeks, maybe 3-4 lectures. However, quantum mechanics is a very wide area, okay? But before we go into quantum mechanics, let's start by reviewing classical mechanics, the type of mechanics we know very well, the type of mechanics we study and in our undergraduate, in our introductory courses, and see, the basics of this classical mechanics, and then later on introduce quantum mechanics so that one can contrast between the two types of mechanics. So classical mechanics is an older mechanics. It's about more than 400 years old, or close to 400 years old. It's back in the 16th century. So in the 16th century, Sir Isaac Newton postulated the 3 laws that came to be the basis for quantum mechanics. The first law states that an object maintains its state of rest or linear and accelerated motion if acted upon by no forces, or forces of zero resultant. So if the total force acting on any body is equal to the zero force, so that is to say there is balance of forces, then this object will stay at rest. And this is the part of mechanics we refer to as statics. Statics is the part of mechanics in which objects do not move, or objects are subjected to zero forces. Then the second important postulate or law of classical mechanics: now if the resultant of the force acting on the object is not zero, so that is to say we have some force F which is non-zero, and this force F acts on a certain object, and it has some magnitude and direction, then the object will have an acceleration. And this acceleration is proportional to the magnitude of the resultant force. And the direction of this acceleration is the direction of the force. So what we are saying now, if the force becomes non-zero, then we have motion, or we have an acceleration. And this is second law, serves as the basis for dynamics. That is the second part of classical mechanics, okay, or the second important component of classical mechanics. So it's either particle at rest, or linear and accelerated motion, or particle is moving, and that is dynamics. Now the third law, which is to every action there is an opposite and equal reaction, and that is a law that deals with interaction between surfaces, between bodies. If bodies are brought in contact to one another, then they exert action-reaction type of forces, and these forces are equal and opposite. This third law applies to dynamics as well as to statics. So this is a general law that applies to two types. So these are the three postulates that were given by Sir Isaac Newton back in the 16th century. Now, the second law is an important one, which is the dynamics law. So what it says is that we have a resultant force. So the sum of all forces, that gives you the resultant force, okay, is equal to the mass of the object times the acceleration. So that means the acceleration is directly proportional to the magnitude of the force. And the constant of proportionality is the mass of the object. Now, this is, if we want to write it in a scalar form, we can write this equation in a vector form. And a vector meaning that writing the letter as a bold-faced letter. So this F here, which is bold, and the sum meaning resultant. So the resultant force, which is a vector, is equal to mass, which is a scalar, times the acceleration. So here we have vector, right, which is the acceleration. It has direction and it has magnitude. Okay, and here we have the force, which is also a vector. It has a direction and magnitude, and we can clearly see that the direction of the force and the direction of the acceleration are the same. Mass m is a scalar, and a scalar does not have any direction. It just has a magnitude. So mass is a scalar. Okay, so that is Newton's second law, okay, which is this relationship here. And you probably know this relationship very well. You probably did a lot of classical mechanics problems in your first years in college, where you utilize this equation. Now we define another quantity, which is a vector quantity, and we call it momentum. And again, you see that it's bold. P, the momentum, is equal to the mass times another vector, which is the velocity. So V is the velocity. Okay, so P, which is the momentum vector, is equal to the mass, which is a scalar, times the velocity. So P and V are in the same direction. Now, the force F, going back to this relation up here, the force F is equal to the mass times the acceleration. And I'm revising here, I'm reviewing. So it's just an overview. I'm not doing rigorously extracting these relations. So the acceleration is the rate of change of the velocity. It's dv by dt. Acceleration is defined as the rate of change of velocity. Or if we think of a mass that is not changing, or the more elaborate or the more accurate form of Newton's second law is to actually take the mass if it changed with time too, and then instead of having dv by dt, you get all the product mv dmv by dt. Now, if the mass is independent of time, then we go back to this relation. If the mass is dependent on time, then you can't get it out of this bracket, and therefore you have to use the definition of the momentum. Then in this case, Newton's second law becomes the resultant force is equal to the time rate of change, or the rate of change of the momentum vector. Okay? One other parameter. So now we know the acceleration, and we know the acceleration is a derivative of the velocity with respect to time. Another important parameter in dynamics is the location, the position vector r. Okay, so the relationships again, the velocity is equal to dr by dt, the rate of change of the position vector. Again, that is known from our studies in dynamics, and the acceleration is dv by dt. So it is so each one, the velocity is extracted from the position vector by taking the first time derivative, and the acceleration is extracted from the velocity by taking the first time derivative of the velocity. The simplest space representation is the Cartesian coordinate system. The easiest that we are accustomed to, the easiest that we know, is a space representation in terms of three mutually perpendicular coordinates, x, y, and z. So any location r, vector r, is written in terms of the components x, y, z in the unit vector directions I, j, k. So I, j, and k are unit vectors in the x, y, and z directions. And these are three mutually perpendicular directions. So x, y, and z are mutually perpendicular, and so this is the system of coordinates x, y, and z, and the unit vectors are I, unit vector of length unity, j along the y direction, and then k along the z direction. So these are the three unit vectors. This system is a right-handed system, RHS. Right-handed system of coordinates is the system if you rotate or if you hold your right hand fingers such that the fingers are curled from the x to the y direction, then the thumb points in the z direction. Or if you use a screwdriver and rotate the screwdriver, put it in the z direction and then rotate it from x to y, then the screwdriver proceeds along the z direction. That is what we mean by a right-handed system. The magnitude of the position vector r is denoted by scalar r, not written as bold, just a regular letter. So this length of a vector r is actually x squared plus y squared plus z squared, meaning if we have this coordinate system and we have some point here, which is a point x, y, and z, and then we have a vector from the origin to this point, and this vector is vector r. Okay, so this is x, y, and z. So the length of this vector r is actually actually equal to x squared plus y squared plus z squared. So this length here, from the origin to the point, okay, where we have point P given by x, y, and z. So the length of this vector r is simply x squared plus y squared plus z squared. What else do we know from classical mechanics? We know kinetic energy. Kinetic is the amount of motion energy, if you like, in a moving object. And this kinetic energy depends on the mass of the object, but it also depends